So yesterday we looked at the instantaneous rate of change, which is the derivative. So today we're going to talk more specifically about the definition of the derivative. So in your packets, please copy down this equation that the derivative of f at point A is the limit as h approaches 0 of f of a plus h minus f of a all over h. So what we saw yesterday, and here's where this equation comes from, is if you have a curve, any graph, and I have a point A and a point B. Point A is at the x-coordinate of A, and B is h units away, so that's a plus h. So the slope between these 2 points is y2 minus y1 over x2 minus x1. So these a's subtract to be 0, which is why the denominator is just h. But that's a secant line. We don't want the secant line, we want the tangent line. So the tangent line is as b gets closer and closer to a, which means that this h value gets closer and closer to 0 when b is really close to a. If we want to look at that as written out, so the average rate of change is the change in y all over the change in x. So the y value here is f of a plus h minus the y value at a is f of a, plug in that x value, all over x2 minus x1. And when you simplify, we get what I have typed in blue. So now let's use that to find the limit of x squared numerically when a is 5, and we're going to let h be 0.1. So the limit as h approaches 0 of f of a plus h, so a goes in for a, minus f of a all over h. So now what we have to do is we're going to let h be 0.1. So I'm not going to use the limit anymore. Instead, this would be like using the chart. So we're going to get close to the actual value, but not the exact value. So this is 5.1, and if I plug that into x squared, 5.1 squared is 20.01. 5 squared, when you plug that in, is 25. When you calculate all this, we get 10.1. So that's an estimate. Now, if we had h actually going to 0, we would get the exact value, but you can't divide by 0. So we looked really, really close, well, not really, really, but just kind of close to 0. Okay, so now we're going to do all this again for number 2. I'll get my definition here. So we're going to use this definition now here for number 2. Finding the equation of the tangent line. So now the equation of the tangent line, remember we're going to use point-slope form. But first we're going to find the derivative, which is f prime of, we want it at 1. So the derivative at 1 is the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Now, let's calculate f of 1 plus h. I'm going to plug that in here. You must keep rewriting this limit. It is part of the equation. You have to keep carrying it down. So I take my 1 plus h and plug it into x. I'm going to take my 1 and plug it into x. Now let's simplify. 1 plus h squared, that's 1 plus h times 1 plus h. Let me do some work here. So you have to FOIL that together, use a method for multiplying. So that's going to be 1 plus 2h plus h squared. Okay, now let's simplify. The limit as h approaches 0. 1 minus 1, that's 0. So we're left with 2h plus h squared over h. Now in my numerator, I can't plug in 0 yet because I can't have 0 in the denominator. But in my numerator, something factors. I can factor out the greatest common factor of h. And yay, exciting, very thankfully, those h's can cancel. If you're doing one of these problems for the derivative with the limit definition, and this h does not eventually cancel, you've done something wrong. Because now I can plug in 0, so I get 2 plus 0, and that is 2. So the derivative at 1 is 2. Okay, so now if we're going to write the equation of our tangent line, that 2 is our slope. We did it at the x value of 1, so that's my x1. So now what is the y value when x is 1? If I go here, plug in 1, and we get 1 squared. So this is the answer for the tangent line. Or we can change the way this looks. I can distribute the 2, add my 1, so that's 2x minus 1. This is an appropriate answer for the equation of the tangent line, or this one. Okay, let's do it all again for number 3. Find the derivative. Okay, so the derivative is the instantaneous velocity, instantaneous rate of change. Let me go back and get this definition. Okay, here we go again. Before I start plugging things into my limit, I'm going to do some work over on the side just to make it easier. I know I'm going to need f of a plus h. So let's find that. That's a is, in this case, 3. So let me replace these with a 3. So f of 3 plus h, let's figure out what that is by plugging it in here. That's 3 plus h squared plus 1. Okay, but 3 plus h squared is 3 plus h times 3 plus h. We have to multiply that together. 9 plus 6h plus h squared plus 1. So then this simplifies to 10 plus 6h plus h squared. So now if I go to plug that in over here, it just makes less writing and work for my limit if I can do this work off on the side. So f of 3 plus h I found is 10 plus 6h plus h squared minus, okay, f of 3, when you plug in 3, that's 3 squared plus 1, which is 10, all over h. So now we have to simplify the numerator. Ten minus 10 is 0. Now we have to factor. Is there a greatest common factor of the numerator? It's h. Now we can divide those. So that's great. So now we can plug in 0. So 6 plus 0 is 6. We found our derivative. 6 is f prime of 3. So now the second half of this problem, find the equation of the tangent line. y minus y1 equals m times x minus x1. Well, 10 is our y1, because that's the value we get when we plug in 3. 6 is my slope, and 3 is my x. And there's my equation of the tangent line. Okay, and our last problem, number 4. The table below shows the x values. And we're going to use it to estimate the derivative at 2. So here's 2. To estimate the derivative, we have to find this slope, the slope between these 2 points. And that value is 12. And then we have to find the slope between these 2 points. And we get 12. So what number are these slopes approaching? Well, they're exactly the same. So the derivative at 2, the slope at 2 is 12. Okay, so in your packet, the next page, it has your homework. It's 1 through 13 odd. Use the remainder of the class time to complete that now.